Probability statistics day number 3. We jump into probabilities using combinations, permutations, a couple other methods. Before we get started, I want for you and a neighbor to think about, let's say you have a bracelet, okay? And you have charms on your bracelet. Okay, you ready? I want to know how many different ways you could put a unicorn. Okay, a unicorn charm. What else? A rainbow. And a Cocoa Puff. A unicorn, a rainbow, and a Cocoa Puff. All right, I want to know how many different bracelet configurations you could have. Go. Okay, we got a unicorn, a rainbow, and a Cocoa Puff. Let's see. Okay. So the first one, we had a unicorn, rainbow, Cocoa Puff. What if I did, I don't like that. Ungroup that. Ungroup. Ungroup. Okay, what's another way I could have them? Okay, how about Cocoa Puff, unicorn, rainbow? Wait, it's the same, right? Because I just swung the C around. So would you agree that this would be the same?
Every combination is in the
Not every. Okay, pause for a second. Could switch them around, right? And I could have the U between the R and the C. Okay, the U between the R and the C, right? That's not the same as the first one. Okay, you're taking a bracelet, you're putting these on there, okay? We're not placing them on there first and then trying to rearrange them because we'd just be running in a circle like a dog chasing his tail. The temptation of the students, oh gosh, come on. Okay, here we go. Ungroup. Screw it. I'm just going to make a new one. Here we go. Right, you got unicorn. What was that? Cocoa Puff, rainbow. I could do that in 2 other ways, right? I could have rainbow, unicorn, Cocoa Puff, or Cocoa Puff, rainbow, unicorn. How many ways to put n objects around a circle? Well, you'd like to say n factorial, right? We would have liked to have said 3 factorial. 6 of them. It's actually not 3 either. It's only 2. We divide by the number because we don't know where it's starting and where it's ending. So we could just cycle it around, right? So there's 3 different ways for us to start it. 3 different ways for us to end it. So if there's 7 people and we want to put them around a table, a circular table, it's tempting to say 7 factorial, which I don't know what that is. 720 times 7, which is a large number. Okay? But then I have to divide by 7, which would make this actually 6 factorial. Oh. Okay? So it's the table problem. We call it the table problem, the bracelet problem, whatever you want it to be called. Okay? If it's circular in nature, we just don't know where it starts, where it ends. So we have to divide it by the number of people. Okay, cool. Let's keep going. Here, I've got a bag containing... Yeah, I am. I am recording. A bag containing 2 red, 3 purple, and 4 green balls. I want to decide, if chosen at random and then not replaced, what would the probability be of choosing 1 green and then 1 purple? So how many green, how many purple? 4 green, 3 purple. How many total? 9. So my first choice, 4 out of 9. My second choice, 3 out of 8. Now this is actually combinations in nature going on, right? So I chose how many of those 4? 1. Out of 9. 4 choose 1 is 4. 9 choose 1 is 9. I chose 3, right, out of, 1 out of 3. I'm choosing one of those 3, but now instead of 9, I only have 8 remaining because it wasn't replaced, which would be 3 times 4 divided by 72, which is 1/6. Cool. I tend to lean toward, when I see something like this without replacement, I lean toward this method instead of the combination method. If that sits better with you, that shouldn't be an 8, that should be a 9. I lean toward, yeah, you get the picture. I lean toward the first method. I don't like to think about combinations, permutations, unless I have to, right? Unless I absolutely have to. Yeah, Wyatt. All right, this is just basic definition of probability. Probability is the number of outcomes of event A over the number of total possible outcomes. The probability of any event will never be greater than 1. It can never be less than 0, but it can equal anything in between. These two events, A and B, in this Venn diagram are mutually exclusive because the union of them is equal to the sum of them, meaning they don't overlap at all. They can't both happen at the same time. So 2 events are mutually exclusive if they can't happen at the same time. All right, that should be pretty basic. Let's get into maybe a Venn diagram problem. Let's sketch some stuff out, what we know. We know the probability of A is 0.6, probability of B is 0.7, but together their probability is 0.9. So right away that tells me the probability of neither would be 0.1, right? How would I go about finding, let's call this region, I don't know, X, region Y, region Z. How would I go about finding any one of those 3? Thoughts? Because I know all of A, so this would be X plus Y. I know all of B, this would be Y plus Z. Say again. 0.9 minus 0.6. Well, what would that find us? 0.9 minus 0.6 would find us Z. 0.9 minus 0.6. Right? I know this entire region here, X plus Y, is 0.6. If I know together they equal 0.9, then I know this Z has to equal 0.3. If I know Z equals 0.3, right here I could say 0.7 equals Y plus 0.3. Therefore, Y has to be 0.4. And therefore, what would X be? 0.2. When you take all these numbers and you add them up, what should they equal? 1. Good. You can check yourself there. Let's take, I don't know, a couple of minutes. Try to find each of those probabilities for A through D. This symbol right here, what does that mean? Not B, or outside of B, or I don't know if is prime used. Is that a word? Yeah. Okay. Okay, so there are your answers. If you're at home and you have no idea what's going on, come ask me or someone in class that knows what's going on. Okay, let's get to this. A committee of 4 is selected from 7 men and 6 women, no restrictions, so it could be all men, all women, or a combination of them, right? Does it matter who is picked first for the committee? No, so you know it'll be a combination. So we have how many people? 13, and we're just choosing 4 of them. Right? I don't know what that answer is, but whatever you get, that'd be your answer. All right, that's the number of combinations or the number of groups, committees that would exist. What if it had to have an equal number of men and women? Well, let's choose from the men. How many are there? How many are we choosing? Let's choose from the women. There's 6, and we're also choosing 2. And we're going to multiply those together, and we'd get the number of possible ways to get 2 men and 2 women in a committee of 4. Okay. This one's interesting. Let's talk first. How would I get a committee of just 1 male and 2 females? Sorry, one male and 3 females. 7 choose 1, 6 choose 3. So that's 1 male. 2 males. 7 choose 2, 6 choose 2. 3 males. 7 choose 3, 6 choose 1. And at this point, I want to stop. I don't want to go to 4 males because that would mean there'd be 0 females. But I want at least 1 female as well in the group, in the committee. So we'd be done. Number of ways to choose 1 male, 3 females, plus the number of ways to choose 2 of each, plus the number of ways to choose 3 males and 1 female. Check. All right? Yeah. A little stressful. Like, just breathe in through your nose and out through your mouth. Just... Order patterns. Okay. I'd like you to take a blind stab at the last one. I'd suggest making a tree diagram if you want to write out BBB, BBG, BGB, BDE. Okay, go ahead, do it however you want, and then we'll check the answers in a couple minutes. Here we go. Child is born. Boy, girl. Another child is born. Boy, girl. Boy, girl. Another child is born. Boy, girl, boy, girl. Boy, girl, boy, girl. That'd be a triple B. That'd be a boy, boy, girl. That'd be a boy, girl, boy. That'd be a boy, girl, girl. That'd be a girl, girl, boy, boy. That'd be a girl, boy, girl. That'd be a girl, girl, boy. That'd be a girl, girl, girl. Hey, probability of 3 boys. 1/8, good. All right, I got 1 out of 8. Probability of 2 boys and a girl. 1, 2. Is that 3? 3/8. Okay. Probability of at least 2 girls. So I got to have 2 girls or more. 1 there. 1 there, 1 there, 1 there. Looks like 1/2. That's how you do the probability using a tree diagram. This right here is called a binomial. Why is it called binomial? There's 2 choices, right? There's choices being made. Now, there are binomial probabilities where maybe it's not equally likely. Flipping a coin over time experimentally, that should be 0.5. So it's binomial with a 0.5. This is about 0.5. I don't know. Does anybody know the statistic is like 0.52, 0.48, or whatever? I don't know. But there are binomial situations where you're making some kind of choice, like does someone have a disease or not have a disease? We're going to get to that later. Right? So likelihood of having the disease, let's say it's like 0.05. Likelihood they don't have the disease would be 0.95. And then we make our tree diagram from there. Okay, so that's the lesson for today. Would we like to do a homework problem? Okay, let's jump into one. I want to do number 19. This one is funky. Number 19, funky. A car can hold 3 people in the front seat and 4 in the back. Yeah, it is. 3 people in the front, 4 in the back. In how many ways can 7 people be seated in the car if John and Samantha are in the back seat? Meaning they can be in any one of the back seats. So let's throw John and Samantha back here. They don't like each other. Looking out the window, just broke up. Okay. I know, it's Heart Week. It's Heart Week. It's not going to last. Okay, anyways. And there's only one driver. So there's always, David is the responsible one. He's always driving. He's like, you guys, I know where to go. I know where to go. Okay, so Of the remaining people, how many could sit in the middle front? 4. Now these two could sit in any one of the back seats, okay? So we'll get there. Okay, so there's 4 people left to sit in the middle front. How many to sit in the passenger shotgun? 3. It does in old cars. Come on, deal with it. Now, we know that John and Samantha can sit in any one of these seats. So how many people are left? 4. So I've got a 4 times a 3 times a 2 times a 1. That looks like I've got 4 times 3 times 4 factorial. And our answer would be whatever that comes out to be. Okay. The wording can be confusing. There's only one driver. Well, yeah, I know there's only one driver. Well, that means that someone pedaling, someone driving. So here we go. And how many ways can 4 women and 3 men be arranged around a circle? We said, based on the bracelet, right, we'd take 7 factorial, divide it by 7 because we don't know where the beginning or the end is. So this would really just be 6 factorial. Oh, we did that one already. That was nice. The next part. Okay, what if the tallest, tallest woman and shortest man? Okay, tallest woman and shortest man have to sit next to each other. So now they have to sit next to each other. How many people are we really organizing? So it's really 6 factorial over 6. So it's 5 factorial. But we could take the tallest woman and the shortest man and swap their spots every time, right? So times what? Times 2. And the answer is written in that right there. Yeah. Yeah, it's real small. A lot of times we sneak the answer somewhere on the page.